Okay, so I'd like to talk about topology and the periodic table of n categories. So remember, the idea is that you can look at n categories that are trivial on the bottom few levels. So if you have just one object and one morphism, one from that to itself, namely the identity, and then one identity morphism of that, up to some number of levels, where the total number of levels here is k. And then you get a lot of further stuff going on up to lots of n plus k morphisms. This is a very special kind of n plus k category. I don't know. This is k, yeah, k morphisms. There's these fence post errors to worry about. We're starting counting at objects are zero morphisms here. So there are n interesting levels and k boring levels below. I probably I could easily be making a fence post error somewhere here, but then that's called a k-tuply monoidal n category. And the reason why it has that scary name is because the concept of a monoidal category, or a category with a tensor product, is a one-tuply monoidal one category. So what it really is it's really a bicategory, but it's a bicategory with just one object, and thus all you focus on are the one morphisms and the two morphisms, which you reindex and call objects and morphisms in your monoidal category, but you can compose objects now, called tensoring them, because they were secretly morphisms from the identity to itself. So what I want to talk about is how this is connected to topology, and how topology, a lot of topology just emerges naturally from this periodic table. So first I want to point out a few ways of hopping back and forth between squares in this table. There are actually a lot of ways, and I won't really cover all of them. So what I covered a lot last time was the idea that you can think of a monoid as a special sort of category, namely a category with one object. That's built into the whole definition of k-tuply monoidal n category. And so we get a map from monoids to categories, and that's called B, because it shows up in topology as well under that name. And it has this funny name that comes from topology, which is called delooping. But what it is in terms of what we're doing right now is that you can think of a k plus 1 tuply monoidal n category as a special sort of n plus 1 category. It's just k tuply monoidal. So the idea is that you're reindexing things so that you're taking your extra monoidal structure and thinking of it as part of your n category structure. So the idea is just that if I have something with one object, well, the simplest example would be this example I'm talking about right here. So you have one object and then a bunch of morphisms between it. You can just think of that as a special case of a general category which has lots of objects and lots of morphisms. So this kind of thing is really a monoid, and this kind of thing is a general category, and B is just the map that turns monoids into categories. So you can do that you can do that throughout this chart. I won't draw all these arrows, but you have them pointing in the same direction at any point. But then I didn't mention last time, but there's also a reverse process called looping, or omega. And so this goes back from n plus 1 cat sub k to n cat k plus 1. And this is a more destructive process. So for example, what you could do, this only, let's see, this only works if you've got enough, to go on. This works if k is at least 1. And so the idea is this. So let me do an example where, like, you've got k equals 2. So you're in a situation where you've got one object, its identity morphism, then a bunch of 2 morphisms, then a bunch of 3 morphisms. So now suppose you had a guy like this, and you wanted to loop it. So what you would do is this. You keep that one object, keep its identity morphism, but now you don't take all the 2 morphisms. You only keep the 2 morphisms sorry. Sorry. Now you only keep the identity 2 morphism, and then you just keep the 3 morphisms going from that to itself. So basically, we've increased the number of boring bottom levels by 1. We had k, now we have k plus 1, but the total number of levels has stayed the same. So this plus this remains the same. So of course, this has to decrease by 1.
So the omegas start in 1 row below where you drew.
Did I draw? Okay, sorry. Yeah, you're right. Yeah, because if I tried to do it to a category doesn't have any particular favorite object to look at the morphisms from it to itself. You could pick an object and do that, but I don't want to get into that. So let's start where we can actually do that reverse process here. Yeah, so you can turn a commutative monoid into think of it as a special monoidal category, but you can also take a monoidal category, take its identity object, and look at only the morphisms from that to itself, and that will be a commutative monoid. And this B process is actually an adjoint of this looping process. So B is a left adjoint to omega. I'm putting it in quotes because these are maps between n categories. So it's a sophisticated concept of left adjoint. But the idea is just that omega is forgetting some stuff, forgetting some things, and B is sort of an attempt to freely put it back in. That's what you expect left adjoints to do. I don't think I'll get into how this is connected to topology, but if you've heard of delooping and looping in topology, that's just really a special case of this stuff. The other process that I talked about, the other pair of processes that I hinted at, go up and down the chart. And so I was talking about this sort of obvious fact that you can think of a commutative monoid as a special sort of monoid, or you can think of a monoid as a special sort of set, and so on. You can think of a symmetric monoidal category as a special kind of braided monoidal category. So we just have this process that's forgetting one of the monoidal structures. So U going from, say, n cat k plus 1 to n cat sub k. So there you had like, maybe like, you had like two monoidal structures, that is two boring levels on the bottom. And then we just say, forget that one and just start keeping track of things here. Well, you probably, if you got rid of this completely, you would probably call these objects and morphisms. You wouldn't call them two morphisms anyway. So we would think of this guy as an object and think of the things from it to itself as morphisms and getting a certain kind of category. So that's another thing you can do. But then that also has a kind of left adjoint. There's a left adjoint which I'll call S for stabilization. And that's a pretty sophisticated one. Because there what you're doing is you're trying to freely put in an extra monoidal structure. And so that I'll call it S, and it's going from n cat sub k back to n cat sub k plus 1. And so, for example, if I have a set, I can form the free monoid on it by just going ahead and saying, okay, let's look at formal products of elements in my set. And I'll get a monoid, which would be like the monoid of words in my set, if my set you think of as an alphabet. And so the idea here is that S is a left adjoint of this U. So those are a couple pairs of processes, and there are actually more, and it gets quite interesting to take. So what you can do is you can take something in the chart, take some category or something that you're interested in, and then start hitting it with these different processes and bouncing it around and getting other kinds of things. So let's do that a bit. So let's illustrate how you get nice things this way. So for example, I could take the category of sets, and there's this S functor going to the category of monoids. And then there's this next S functor going to the category of commutative monoids. So I could take, for example, a set with n elements and then apply this first functor. So I'd get the free monoid on n generators. And as I said or hinted before, you could also think of that as like the set of lists of elements of this, or words, so lists of elements x1 through xn. I think computer scientists are much more fond of free monoids than mathematicians are. So mathematicians like free groups and don't talk about free monoids much. And for computer scientists, it's sort of the reverse. List. Sorry?
Ring theorists like monoids.
Okay, good. Well, yeah, that's right. But you throw in addition just to make sure you have a group around, right? Yeah, but the multiplicative monoid is a very nice thing. Yeah, that's right. Yeah, so that's true. And then here we do it again, and we get the free commutative monoid on n generators. Well, that at least is beloved by mathematicians, because you could call that the natural numbers to the n with addition as the monoid operation. So that's how this kind of thing goes. But let's try a slightly fancier version of it. Let's go to the next column in the periodic table and do the same kind of thing. Keep going down it using S and see what sort of stuff we get. So this is interesting enough that that I'll just do it starting with the very simplest category, or the second simplest category, and see what we get. By continuing to stabilize it. So what I meant by the second simplest category is the category that has one object and its identity morphism. The simplest category would have nothing at all, and that's not going to be too much fun. So we'll take this guy here. We'll form the free monoidal category on it. So this had just as one object. Now when you freely generate a monoidal category says you can tensor objects. So we get a bunch more objects. Maybe I want to give this some other kind of name like X. So now this will get a category that has objects that look like tensor products of copies of X. And it doesn't have too many interesting morphisms. It's true that you get isomorphisms called associators that involve changing the parentheses around in this expression, but those are sort of bland in a certain way. And in particular, you can never get a morphism from X tensor itself n times to X tensor itself some other times. So if you draw the morphisms as a kind of a picture where you actually think of all these x's as dots on a line, then the morphisms will just be sort of boring kind of braid-like things that just goes straight down. So basically what you get is a category that's equivalent to what's called the discrete category on the natural numbers. So the idea is that the objects are just the natural numbers, and then the only morphisms between them are identity morphisms. So this category I'm describing now will be equivalent to what you get if you put in all those associators and stuff. There's a notion of equivalence of categories that lets you sort of simplify what you've got here. So what we get is that this is going to be the empty set if n is not equal to m, and then it's just a one-element set. The identity if n is equal to m. So that's pretty boring. But the picture is actually mildly interesting because of what happens next. So I'll draw that picture again. Because now if we form the free braided monoidal category on that monoidal category, then what happens is that we are throwing in a braiding. And remember what the braiding does is it lets you switch things. So actually we should really draw this picture now not in 2 dimensions but in 3 dimensions, and think of our x's as dots on the top of a 3-dimensional cube and also on the bottom. And it's still true that you can only get morphisms from X tensor itself n times to X tensor itself the same n times, but now there are more interesting morphisms because you can start braiding these guys around. This is related to how braided monoidal categories are sort of like commutative monoids, but you keep track of the process of switching 2 things around. So you can get lots of interesting morphisms now. So that's a picture of a typical morphism in what we're getting now. This category that we're getting now, I guess it's often called like the braid category. It's often called the braid groupoid. A groupoid is a category where every morphism is invertible, and this is one like that. So basically the objects are still the natural numbers. You can take them to still be the natural numbers, but now the Hom sets are a lot more interesting. They're empty between two different numbers, but now if they're the same number, you get a whole interesting group of morphisms from that object to itself, and that's called the n-strand braid group. And that shows up a lot in topology. So it's a group where the elements are braids and composition or multiplication is sticking one braid on top of each other, another. And that's a really interesting group. Then we can go another step forward and we get something, well, you could call it the symmetric groupoid, but the idea is that when you go from a braided monoidal category to a symmetric monoidal category, the new fact you're putting in is the equation that says the two ways of switching two things now become equal. That's a law in the definition of symmetric monoidal category. So what this S functor does is it just imposes that extra law, and so then instead of getting braids as morphisms, you just get permutations, because we're saying we don't care whether we switch something in front of something or in back of something, we just care that we switch them. So we get here a category where the objects are the natural numbers again, but now the Hom sets are quotients of the Hom sets we had before, so they're still empty if n is not equal to m, but now we get the symmetric group Sn if n is equal to m. So this is the symmetric group, the group of permutations of n things. So you could call this groupoid the symmetric groupoid because it just contains all these symmetric groups as its Hom sets, but probably a more familiar name is you'd say it's the groupoid of finite sets and bijections between finite sets. So you can take the category of all finite sets and all functions between them, and then just look at the invertible functions, that is the isomorphisms, and that's called taking the core. I mentioned this, I think, in my first lecture. That's called taking the core of the category of finite sets. You get the groupoid of finite sets. So you see we got a lot of interesting and very famous stuff just from starting out with the most boring thing, second most boring thing in the world, and just stabilizing it. So we get three-dimensional topology, braids. Then we get basically four-dimensional topology, but in four-dimensional topology you can untie all knots so it simplifies and you just get permutations. But you get the famous groupoid of finite sets showing up. So basically this is like finite sets, sort of, but where you care how you move the elements around each other. And when you get into higher dimensions, you don't care. So like electrical circuitry would be much more simple if we were living in 4 dimensions, because wires would never get tangled up. And then if you have further extra dimensions, nothing new happens. It's just stabilized at that point. Okay, so now let's go on to some other thing you can do with this business. So I'm going to be interested now in n-groupoids. So what are those? So in an n category, first I'll tell you, I'm going to define the concept of an equivalence in an n category. So an n morphism, say f from x to y, is an equivalence if it has an inverse. So a morphism going back that's an inverse in the usual sense. But then we want more subtle concepts, namely we proceed inductively going down from the top. So a J minus 1 morphism is going to be an equivalence. Well, we don't demand that it have an inverse. Not exactly. We just want a morphism, let's call it f bar, going back from y to x, which is an inverse up to equivalence. So what does I mean by that? So, meaning that we have equivalences, say alpha going from a suitable identity to f bar f. So in other words, I'm not saying that f bar f is equal to the identity. I'm just saying that it's equivalent to the identity. And I know what that means because we're proceeding down inductively, and we started out saying that an n morphism is an equivalence if it has an actual inverse. And that lets us define what it means for an n minus 1 morphism to be equivalence and so on. So we want that, and then also we want one going the other way. So that's a downwards induction. So you can say an equivalence is something that's invertible up to equivalence, and that's not circular because, well, you ground it or sealing it by starting at the n-dimensional case. So then you define an n-groupoid just to be an n category where everything is an equivalence. So where all J morphisms for all J, that is for all J between 1 and n, are equivalences. So these are the best studied class of n categories. And in some sense, they were studied before people knew about n categories. And when Grothendieck wrote this big manuscript pursuing stacks, where he was starting to study n categories, these were his motivating examples. And the reason why is that there's a theorem. I'm stating very few theorems in this course, and proving far fewer. But this is actually a theorem given like Batanen's definition of n category, which is that any topological space gives you an n-groupoid. Any topological space X gives, let's just say, has something called the fundamental n-groupoid. This is a grand generalization of the fundamental group of a space. So we'll write it with a capital pi n of x. And the way it works is this. The objects are just the points of x. Then the one morphisms are just the paths in x. So if I have a path from x to y, I'll just think of that as a morphism, and we know how to compose paths. And we also know that we can guess what the reverse, this f bar thing would be the reverse path, the path going back the other way. And then two morphisms. Well, you could call them homotopies, but I think I'll call them like paths of paths. I have to be a little clearer about that. So the idea is I have a path f from x to y and a path g from x to y. What's a two-morphism between them? It's a one-parameter continuous family of paths with fixed endpoints interpolating between those two. And so it goes on like that. And then when you get to n-morphisms, then you clamp down. What you do is they're going to be homotopy classes of these, I'll call them n-fold paths, by which I mean paths of paths of paths of paths, where you say that n times. So homotopy means that you can like continuously deform while keeping the things with the ends fixed. And so here we're modding out by an equivalence relation where we count homotopic things as the same. And the reason why we're doing that is because we want the n-morphisms to compose associatively on the nose and have inverses on the nose. There's nowhere, you can't, the buck stops here, right? Before, we could say like, oh, this f bar is like f but going backwards. It's sort of like an inverse. It's not really an inverse, but f bar is connected to the identity by a path of paths, and so on and so on. But here, you need strict inverses for something to be an equivalence, and so that's why we cut it off like that. Of course, you can try to never cut things off, and then you'd be dealing with infinity groupoids, which is perfectly fine, but that's just not what I want to talk about right now. So now there's this interesting, there's a couple of interesting conjectures about this idea. So one big kind of conjecture-like thing, the homotopy hypothesis, says that in some sense, n-groupoids capture all the information in the topological space if you're a homotopy theorist. So like a topologist is someone who can't tell the difference between a donut and a coffee cup. I guess a homotopy theorist, we heard from Clark Barwick yesterday, someone who can't tell the difference between a point and a line. Right? So it's like a further disabled type of mathematician and their inability to recognize things. But that simplifies life a lot. And that's why it's fun. So spaces up to homotopy are supposed to be completely classified by their fundamental n-groupoids, if they are spaces that have nothing exciting going on above dimension n, I should say. But instead of getting into that, let me state a kind of simpler conjecture related to that, which is that if you do this to the sphere, so let's look at pi n plus k of the n sphere. This is the free n plus k category on an object x and an equivalence and an n-morphism that's an equivalence. And what is this n-morphism? It's going from the identity of the identity of the identity of x to itself. You don't know how many ones I wrote there, but you do actually, because I said this is an n-morphism, so there's got to be, I guess, this thing has to be an n minus 1 morphism here. So why should that be true? So let me not do the case. Let me not do the simplest case, which is the circle. Let me just dive right in and do the 2-sphere. So let's look at pi sub 2 of S2. So what is that thing? So that's supposed to be the free 2 category or bi-category on an object, and then, well, it has its identity morphism, but then this is supposed to be free on that object and on this two-morphism. I'm keeping track of the indices for you. It's hard. You have to translate some numbers to check here. But so this thing, and this is an equivalence. So that's sort of what you start with, and then we look at the free bicategory. So we're looking at the free bicategory on this thing. So what do I mean free bicategory on this? Well, starting from this, we can start composing it with itself. We can compose it both in this vertical direction like this, and in this horizontal direction like this. And it turns out that what you get is that all you get, the only two morphisms that you get, will all be f to the n for some various n. Because that interchange law lets you turn the horizontal compositions into the vertical compositions. And so all you get are things like this, where n could actually be any integer, because f has an inverse. So we could have f to the negative 1 as well, and then its powers. So what I'm saying here is that if you look at all the two morphisms, which all go from one star to itself, they form a group, and that's the integers. Now, in this game, it turns out to be very interesting to look at this kind of group, where we go up to the very top dimension, which is 2 in this case, and we look at the morphisms from an identity to an identity in that top dimension. And that has a name. In topology, that would be called pi2 of S2, the second homotopy group of S2. So if you like, you can take this as a definition of the second homotopy group, or if you know about homotopy groups, you could take this as a claim. I mean, this is a known fact, but take it as a claim that this is how it should work. So why does this have to do with the two-sphere? We should draw the picture a different way. Think of this one object, well, it's a point, but then think of this identity 1 star. Remember, it's like an identity path from that point to itself, but so identity path is one that doesn't go anywhere. So it's very hard to draw a path that doesn't go anywhere, so I'm having it go a little somewhere. But then the fun starts when we look at this two morphism from that to itself, and here's what that looks like. This is a sphere, and what I've done is I've taken this thing here and I've attached the bottom edge to the top edge, because they're the same, right? So F now looks very grandiose. This two morphism F looks like that, and that thing looks just like a two-sphere. So that's the idea why this kind of thing should sort of described using categories should be related to the sphere. And that works in higher dimensions too. So one thing you could say, by the way, is that this is what I call B of the integers. So the integers are a group, i.e. a monoid. This is the one object category that they're associated to, and this is the two category that they're associated to. If you remember what that B thing was that I described at first. So this is a way to say what I said up here. And then this goes on. I'm running out of time, so I'll just sort of say, like, similarly, you could, that works in higher dimensions. But it really gets fun when you, so far I'm just looking at k equals 0. That is, the index down here is matching the index up here. But the cool thing about spheres is that they have non-trivial homotopy theory above their visible dimension. And the first example of that is pi3 of S2. So let's think about that. But we're going to think about the fundamental 3-groupoid of S2. So it's like this story here, except instead of just creating a bi-category out of this data, we're going to create a tri-category out of this data. So it's the free tri-category on this thing. And then we get some interesting new stuff happening. So we'll have, for example, here we get some things like this. We have this identity two-morphism, which is sort of boring. But remember, I said that this F here is going to be an equivalence. And so there was this F bar that was acting sort of like an inverse to it. In particular, there was this, it's not that F bar is really equal to the, it's not really the inverse of F, but there's this higher morphism, which turns out to be a three morphism, which I called alpha, going from the identity to FF bar. And that's an equivalence by the way we require things. So we have an equivalence like that. Then you may remember from previous lectures that we had some sneaky games we could play using the interchange law, which let us do things like move the F and the F bar around each other. So this is not necessarily equal to this now, but it's still, there's an equivalence between them. And we can keep on going like that. I did this argument before until you actually get all the way around to having switched them, switched the order of them. This is where the braidings are coming from in the first place. But then now what we can do is that this composite of F and F bar is also equivalent to the identity, and I guess I called this thing beta bar. So we can get back down to an identity. So we have this very non-trivial, well, you can't tell really if it's trivial, but it looks like it could be non-trivial, three-morphism from the identity to itself. And if you draw it in a different style of drawing, you'll see perhaps better what it looks like. So we're talking about a tri-category here, so it's good to draw pictures in 3 dimensions. And what's going on is that we're starting out with the identity on top here. And then F and F bar get created, appear out of thin air via this three-morphism alpha. Then they trade places. And then they annihilate each other. They cancel each other out. If you're into physics, this should make you think of antiparticles and such, and it's actually related. But the main thing I want to talk about now is that this three-morphism is not the identity three-morphism. So there's some exercises that you would have to do to really, which I don't have time to do, but sort of are crucial. So one thing is to show that this is not equal to the identity morphism, which would be drawn by showing nothing at all. And it's also not equal to this kind of thing where you just create the F and the F bar and then annihilate them, but without switching them. And so, I mean, you have, that takes work to do. But then you can also show that if you have complicated looking three morphisms, more complicated than this, you can always reduce them down to to fairly simple ones. For example, you can show that if you have a piece of your picture that looks like this, so we could have some big complicated bunch of stuff, but a portion of it looks like this, you can show that it's equal to this. That's actually very easy to see because this thing here is, if I get it correct, it's what I called alpha. Maybe if I get it wrong, it's what was beta. And this is alpha inverse. And so we're just canceling them out, and that's true. So if you have something like, so we can make up a three-morphism. We can make up all sorts of fancy three-morphisms. For example, we could make up one that looks like this. Two of those guys next to each other. But then you can check, using the laws of a braided monoidal category, that you can actually move one of these guys on top of each other, and you get the same thing. This is basically using the interchange law, actually. And then you can use this kind of law here to connect them up to each other. Sorry. Yeah. I did something wrong. I want all my twists to be twisting the same way around, like that. So I'm using this law here. So it turns out that you can show that all the three morphisms in this three category are just things like this, where you have n twists. So the only three morphisms in pi 3 of S2, they're all equal to ones that look like this, where this number n, well, here I drew a case where n is positive, but it could also be negative, and then the twist would be twisting back the other way. So in other words, what I'm saying or claiming is that if you look at the, so these are the only three morphisms, I should say, from the identity to itself. From the identity to morphism to itself. There would be other ones that start and end at some power of f, but we're not talking about that. So what I'm saying is that this thing is just the integers. This group is just the integers. And this group of three morphisms going from the identity to morphism to itself, that's pi 3 of S2, the third homotopy group of the two-sphere. In this categorical approach, that would just be the definition of it. But you can check that that's the same as the topologist's usual definition. So homotopy groups of spheres basically are what you get when you start examining these free n categories on a single equivalence at some dimension. And I wanted to go ahead, but I think I'll answer a question. So one can go ahead and have more fun with these games. Yes?
I should have asked this earlier, but when you say that the category is free, that's what property that it satisfies with?
I mean, yeah, so so if I say, yeah, that's sort of tricky. So the loose hand wavy answer is that if you say, like, I want to generate a three category that's free on some stuff, what it means is that you just start using the laws of a three category to build up everything you can from that stuff, and you impose all the equations or put in all the isomorphisms that the definition of a three category requires that you do, and you don't do anything else. So I mean, that's probably the most useful answer. Of course, to prove something that is a free gadget of some sort, it helps to have other ways to think about it. And in category theory, we like to describe free things using left adjoint functors. So a right adjoint functor tends to forget information, and then a left adjoint functor is something you can rigorously define, but what it has the effect of, typically, often, is that it freely throws back in that stuff. So to give you a really good answer, I would need to say which adjunction I was talking about here. But and I did talk about a few adjunctions earlier in the lecture, but not the one that's needed for describing this one. Yes?
So I have 2 questions from Zoom. First from Malta Sporring. Do you have a version of Freudenthal suspension theorem in this setting? And you might want to repeat the question to the mic.
So the question is, do we have a version of Freudenthal's suspension theorem? And yes, that is just the stabilization. That's subsumed by the stabilization hypothesis. So the stabilization hypothesis says that as you keep applying S and marching down the column of the periodic table, it stabilizes when you reach to the k, sorry, when k is n plus 2. And that actually, the Freudenthal suspension theorem was one of the main reasons we guessed that that was true. Yeah.
Okay. And then the second question from Jeff Basil. Sorry in advance for the annoying question, but there seems to be a proliferation of n's and k's attached to the outside of the n categories. And then we seem to be doing ordinary things like adding 1 to them, etc. What are we supposed to do about all these uncategorified numbers hanging around? Do they have an exemption? You can try repeating that question.
Yeah. The question is like, why am I not categorifying everything in my lecture? Why am I using ordinary natural numbers instead of finite sets or something like that? One reason why I'm not doing it is that to categorify everything takes a long time, right? That is, categorification is a process of systematically replacing equations by equivalences, and I already gave another example that, like, when I categorified the definition of category and got the definition of bicategory, if I'd looked at it a different way, I said, oh, wait a minute, I forgot to do this, and then I could have gotten the definition of double category. Now, in this particular case, I have no idea how you would categorify those particular n's and k's. So that's another reason why I didn't do it, is because I have no idea how to do it. But there might be a way to do it, but I really haven't thought about that. Yes?
You phrased the statement about fundamental groupoids of spheres as a conjecture.
Uh-huh.
What's hard about turning it into a theorem?
Part of what's hard about it is that there are a lot of different approaches to n categories. So I've been sort of pushing ahead with Batonen's approach, which is the one that's globular in nature rather than simplicial or something else like that. And so in Batonen's approach, people have they've set up the fundamental n-groupoid of a topological space. But what they haven't proved, for example, is that there's some sense in which n-groupoids are the same as homotopy n-types. And so you would like to prove, you'd like to prove they're equivalent in some manner. And one sort of cheap manner that people often do is they try to show that you have an equivalence of model categories of the two kinds of things. Once you did that, then you would know, roughly speaking, that anything you already know in topology you get to use for n-groupoids. And then I suspect it would be, I'm not sure, but I suspect it would then be fairly easy to prove this. But nobody has actually yet shown that result for Batonen's n categories yet.
I see. So it's at that level, rather than for spheres showing that that you actually get something freely generated by like this finite bit of
There would probably be some extra work, but it wouldn't be so much about spheres particularly. So yeah, so you would, to prove this in the royal manner, you would want to show that when you're building CW complexes by sticking balls together, that there's some corresponding thing going on at the level of the n-groupoids, and then you can use a decomposition of the sphere and get this. Yeah.
Can I offer a perspective on that?
Sure, yeah. Yeah,
So-
Tom has worked on this stuff.
Yes, and one answer is that, of course, it depends on your definition of n-groupoid, and there are some definitions that would come close to making it a...
Talking to
I'm not
the-
going to speak into your chest, Jay.
Don't talk into my chest.
There are some definitions that would almost make it a tautology. I mean, there are various conjectures about how the notion of n-category relates to the notion, relates to topological notions, and if you make your definition of n-category sufficiently topological, then it becomes easier to prove these conjectures, but then you're some distance from the algebraic point of view, so yeah.
Yeah.
Before we stop recording, and I guess we should probably finish now, do you want to tell everyone, including
Yes.
people on YouTube, when we're continuing?
Right. So I'll tell you, we're not continuing next week, and we're not continuing the week after that, but don't do a proof by induction. We are rejoining the week after that.
2nd of November.
The 2nd of November, we are coming back. So I'm going down to Cambridge, and then the week after that, there's going to be a big festival at the ICMS celebrating the 30th anniversary of the ICMS, and Graham Siegel is going to be giving a talk there at 3:30, and I wanted to go see it and not stop other people from seeing it. That's Thursday after next week. Yep. Okay, thanks.